Hello everyone, this is Dr. Sreelakshmi, working as an assistant professor in AMN, Institute of Aeronautical Engineering. In this lecture, I will discuss about Hamiltonian Path and Hamiltonian Cycle. In previous lecture, we discussed Eulerian Path and Eulerian Cycle. Eulerian Path and Eulerian Cycle will be concentrating on only the edges. No edge should be repeated more than one time. Here in Hamiltonian Path or Hamiltonian Cycle, we are concentrating only on vertices. It means each vertex need to be visited only once. Hamiltonian Cycle. A cycle in a graph G that contains every vertex of graph is called a Hamiltonian cycle. And here, a path that contains every vertex is called Hamiltonian path. A graph that contains Hamiltonian cycle is called Hamiltonian. Here a slight difference is there between Hamiltonian path and Hamiltonian cycle. What it is? A path that contains every vertex is called Hamiltonian path. That is a standard definition. And here we will concentrate that a vertex which we are selecting as a starting point may not be the ending point for Hamiltonian path. We will see an example. Let me take a graph where it is having A, B, C, D, E, 5 vertices. As per my definition, a Hamiltonian path is a path that visits each of the vertices once and only once, but can begin, end on different vertices. So now I'm going to start at vertex A. I'm going to travel through B and then to E and then to D and then to C. Here, the vertex should not repeat as per the definition. So each vertex is visited only once. A to B, B to E, E to D, D to C. Here, the Hamiltonian path exists as A to B, B to E, E to D, D to C. Each vertex is visiting only once. There is no repetition of the vertex. And here, if I want to close this, from C to B, if I travel, then vertex B is visiting twice, which is not the condition. The condition is each vertex should repeat only once. It should visit only once. So, there is no Hamiltonian cycle. We have only Hamiltonian path. Second point, a graph that contains an Hamiltonian cycle is called Hamiltonian. It means here the starting vertex and the ending vertex should be same. Here is a question. The vertex, wherever we will start, we need to end at the same vertex. We feel that vertex is repeating twice. It is not like that. Here they are mentioning from A we are starting and to A we are visiting. So leaving and entering, both are happening only once. For this, we will see an example. Before that, we will see the properties of Hamiltonian graphs. The first point, graph must be connected. No vertex should be simply ideal or isolated. So all the vertices should be included in the graph. Second one, no vertex of G can have degree less than 2. So each vertex should have edges 2. Third point, G cannot contain a cut vertex, that is, vertex whose removal disconnects the graph. As we know, the cut vertex, if you take any graph like this, I'm going to name it as A, B, C, D, E, F. This is a graph. Now, the third point, G cannot contain a cut vertex. That is, a vertex whose removal disconnects the graph. See, if I want to remove D, E, F, then there is no problem because I'm having this A, B, C. This is fine. Now, I will take one more example where A, B, C, D are connected like this. If I am removing this particular vertex, if I am removing this particular vertex connection, then this is not said to be a Hamiltonian because there is no closed loop. There is no closed loop. So, this is a condition. And fourth point, if G contains a vertex X of degree 2, then both edges incident to X must be included in the cycle. So altogether, we should remember that the vertex which are present in a graph should be connected to the vertex of other, where it is having two edges, or we can say the degree of the vertex should be 2. And G cannot contain a cut vertex. If it is so, then the graph may not be complete. So these are basic properties of Hamiltonian graphs. And next, we will see two rules here. We can also consider these two rules as properties. And here, the rule 1 is, if two edges incident to a vertex X, and this X must be included in the cycle, then all other edges incident to X cannot be used in the cycle. So for example, I am going to connect here from A to B and from A to C. And if I want to connect one more, then A to E. This should not be the case. Here we can connect from C to E or from E to B and B to C. If I want to connect, then A to E, here the condition will not satisfy. If two edges incidents to a vertex X, here A is the vertex. The two edges incident to the vertex are this E1 and E2. These two are incidents to the vertex A. If the other edges incident to X cannot be used in the cycle. If for example, I am going to connect this A to E, and here see, from A to C, C to E, E to A, there is a loop or there is a cycle where it is not including this vertex B. So this should not be happened. That is rule 1. And rule 2. If in the process of attempting to build a Hamiltonian cycle, a cycle is formed that does not span G, then G cannot be Hamiltonian. The rule 2 indicates the same thing, where we should not have internal loops. We should visit all the vertices and then only we need to complete the cycle. See here, from A to B, from B to E, and before visiting this C, I should not close this loop. So where I will exclude this edge and I will travel from E to C, that is, I will visit from E to C, and from C to A we will traverse. So that here is a Hamiltonian cycle A to B, B to E, E to C and C to A. This is the correct possibility of finding out the Hamiltonian cycle. Before visiting all vertices, we should not close the cycle. That is rule 2. And now we will see few examples for Hamiltonian path and Hamiltonian cycle. So as we discussed in the previous slide, a Hamiltonian path is a path that visits each of the vertices once and only once, but can begin and end on different vertices. This is a possibility of finding out the Hamiltonian path. You can start from any vertex and you can end at any vertex. And now this is an example for Hamiltonian cycle. So now a Hamiltonian cycle is a path that visits each of the vertices once and only once and ends on the same vertex as it begins. So now I am going to start from A to B, B to D, D to C and C to A. So my internal path is A to B, B to D, D to C and C to A. Where we started, we are ending to that vertex. Here, possibilities are there. We can start anywhere in the graph. So, how many possibilities are there to have these cycles? For that, a formula is there to finding out the number of possible ways, that is n minus 1 factorial. N minus 1 factorial ways. Here, n indicates number of vertices. Now, the vertices here are 4. 4 minus 1 factorial ways. That is 3 factorial. It means 6 ways are there. 6 Hamiltonian cycles are there internally. So we can start from any of the vertex and we can end. This is an example of such kind. This is possibility of 1. Possibility of 1 way. One more possibility will be there. Like that, 6 possibilities are there. And we will see one more example, Hamiltonian cycle. To find Hamiltonian cycle, I am naming the cycle A, B, C, D, E. 5 vertices. And naming the edges is not required. Since there is no condition on edges, I am not going to highlight the names of the edges. If we want, we can highlight the edges also, like E1, E2, E3, E4, E5, E6, E7, E8, E9, E10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So naming of the edges. And now 5 vertices are there. I want to find out the Hamiltonian cycles. As per the definition, each vertex should be visited only once. And here, this is a formula where we can find out n number of ways. Hamiltonian cycle, finding out the ways. So here 5 vertices, 5 minus 1 factorial ways, that is 4 factorial. It means 4 into 3 into 2 into 1 ways, 24 ways. So in this graph, we can find out 24 Hamiltonian cycle possibilities. One of the possibility we will find out from A to E, E to D, D to B, B to C, and C to A. So here the possibility, first possibility A to E, E to D, D to B, B to C and C to A. The starting and ending vertices is same. And each vertex visited only once. Here, starting and ending vertex is A. So we should not say that vertex A visited twice. It is considered as leaving and entering. Leaving from the vertex A is 1, ending to the vertex A is 1. So this is one possibility. Similarly, you can find one more possibility, that is you can start from B and then you can execute. Or you can start from A to B, B to C, C to D, D to E, and E to A. This is one more possibility. Like this, we can find out 24 ways. So 24 Hamiltonian cycles are present in this graph. But it is not possible to find out all the 24 ways at a time. So here are the two possibilities where we discussed. And now one more example for semi-Hamiltonian graph. A semi-Hamiltonian graph is a graph that contains a Hamiltonian path but not a Hamiltonian cycle. These problems are for competitive exams. They will give a graph and they will ask to find out the path but not a cycle, or vice versa. So a semi-Hamiltonian graph is a graph that contains a Hamiltonian path but not Hamiltonian cycle. So let me check possibility of finding out the Hamiltonian path. It means we need to start at the vertex, any vertex, and we will end to other vertex. So from A, I'm going to start here, A to D, and D to C, C to B, and B to E. So here 5 vertices are there, A, B, C, D, and E. Each vertex visited only one time. And the starting vertex is A, but the ending vertex is E. So here we have Hamiltonian path, but there is no Hamiltonian cycle. Since A and E are not connected with each other. Here A and E are not connected. If there is a path existing here, then we can close this cycle. We can find out the Hamiltonian cycle. And this graph is only for Hamiltonian path, not for the Hamiltonian cycle. If I want to end at vertex A, I should traverse through any one of the vertex, and it might be a reason to visit that particular vertex 2 times. So where the condition fails. So here what I did, from A to D I traversed, and D to C, C to B, and B to E. This is one possibility of finding out the Hamiltonian path. Next example is a graph semi-Hamiltonian. We need to check as we know the conditions. I will start from A to E, E to D, and D to B. So here there is no possibility to find out the semi-Hamiltonian because the vertex D is in center. If I want to traverse for the rest of the vertices, if I want to traverse or if I want to visit the rest of the vertices, I need to visit vertex D 2 times or more than that. See here, we will check once, A to E, E to D, D to B, and again I need to return back to D to visit G. And to visit C, I need to travel from G to C. If I want to visit vertex F, I need to traverse this G one more time and then I need to visit vertex F, where D is visiting 2 times and G is also visiting 2 times. So where the condition fails. Each vertex should visit only one time. So here the graph given is not a semi-Hamiltonian. And we will check with second figure. A to C, C to D, D to E and E to B. Here it is possible. Each vertex visited only one time. So A to C, C to D, D to E and E to B. No vertex is visited twice. So this is a semi-Hamiltonian graph. And two more examples to find out the semi-Hamiltonian. A to B, B to E, E to D and D to C. Even in this particular graph, you can see this will close the graph, where it can also say that it is an Hamiltonian cycle. A to B, B to E, E to D, D to C, C to A. Both Hamiltonian path exist and Hamiltonian cycle also exist. And next figure. Now here I'm going to start at vertex A to B, B to C, C to D, D to E. So all vertices are visited once. So the graph is a semi-Hamiltonian. And if I want to find the Hamiltonian cycle, then vertex B need to be visited twice. So here there is no Hamiltonian cycle, but Hamiltonian path exists. And the questions we will be asking in examinations like, determine if each of the graphs below are Hamiltonian. So for those that are, find a Hamiltonian cycle. So here all the vertices are within the graph. That is, they are connected with each other. So this comes under the first condition. The vertices are connected with each other. Graph G is connected. And the second figure is also connected. So both are satisfied, the first condition. And now I want to find out the Hamiltonian cycle. This is my question. Find a Hamiltonian cycle. So let us start from the vertex A. We will check the possibilities. So A to B, B to F, F to C, C to E, E to D, D to G, G to H, H to A. So fine. Here is a possibility. First possibility, A to B, B to F, F to C, C to E, E to D, D to G, G to H, H to A. The starting vertex is A. The starting vertex is A and the ending vertex is also A. And all the remaining vertices visited only once. So the first figure is an Hamiltonian cycle. And second figure, we will check here. If you see carefully, from A to F, F to E, and then E to J, J to K, K to L, L to C, C to B, B to H, H to I to D. See, once if I select this particular path, we are unable to visit vertex G and we are unable to come back to A. So where the condition for Hamiltonian cycle is, we need to start at a particular vertex and we need to end to that particular vertex. So this possibility is not correct. So we will check for one more possibility whether it is existing or not. So I will start from A to F, F to E, E to D, D to I to G, G to H, H to B, B to C, C to L, L to J, J to K, and K to A. Yes, here is a possibility that this particular graph contains Hamiltonian cycle. Our analysis should be done in multiple ways. The first possibility where I couldn't find out the Hamiltonian cycle because I'm unable to visit vertex G and I'm unable to close the cycle since the starting and ending vertex should be A. But here, when I attempting second time, I'm finding the another possibility where I started from A to F, F to E, E to D, D to I to G, G to H, H to B, B to C, C to L, L to J, J to K, K to A. The starting vertex is A and ending vertex is A. So each vertex is visited only once. So where there is an Hamiltonian cycle existing in this graph. So this is about Hamiltonian cycle and Hamiltonian path. So the content is taken from this textbooks and the resources available in the online. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.